Hello, nice to meet you all. This is Wei from Alibaba Damo Academy. On behalf of Team Together, today I'm going to present our method in CityLearn Challenge. Basically, we propose an ensemble approach of forecasting, optimization, and reinforcement learning. In this challenge, we have data from a community with multiple buildings, such as electricity demand and solar generation of a full year. Resource management can be performed by directly using solar, charging or discharging the battery, or relying on the grid. We aim at providing decision support of energy storage devices, that is to say, to decide the hourly battery charge or discharge. Here we observe two key issues. The first one is the uncertainty of solar generation and load, as they are either influenced by the weather condition or be fluctuated with respect to the hour of day. And the second issue is the multi-objective task to achieve economy, low carbon, and grid stability at the same time. To tackle these two issues, we propose a solution of two-stage dispatch. So firstly, we forecast the future load and solar generation, then perform the battery dispatch based on the predicted values. Let's first focus on stage 1. We train a tree model, a sequential neural network, using the training dataset. Important features are the building time series data and the external features including the weather forecast. Then we apply the trained model to infer the predicted values of load and solar generation respectively. As example in the plot, the black curve represents the real value of a load for a period, and the red one is the corresponding predictions. Generally, the trend has been successfully fitted, only with sort of biases due to the data drift issue, etc. Next, to provide decisions of battery dispatch based on these predictions, we follow two branches of methodology according to the literature, including the reinforcement learning and stochastic optimization in parallel. The first method is reinforcement learning, where we train the agents to interact with the environment, and they learn to take the actions according to the observations. Here in the plot, we provide the basic model architecture. To look in details, the environment is the same as CityLearn simulator, and we introduce essential features including weather, solar generation, load, and their predicted values to enhance the observations. In terms of pre-processing, the observations are filtered and normalized. And in the procedure of post-processing, we mask the action space according to the battery constraints and the state of charge of buildings. Last but most importantly, we train the multi-agent reinforcement learning algorithm to achieve the building coordination as defined in the objective of price cost and grid cost. And here it is, MAPL algorithm. So considering the number of agents is different across 3 phases, we propose a training strategy with global information of all buildings, as well as distributed execution strategy for each building. More precisely, as illustrated in the formulas, an agent learns its own policy while we maximize the expected discounted accumulated reward globally. In addition, to incorporate the homogeneity of agent structure, we perform parameter sharing among the multiple agents, which consequently we also improve the generalization ability. Now we switch to the other methodology for battery dispatch, which is based on the model predicted control. Firstly, we extract the optimization objective and the battery constraints from the CityLearn environment, that is, the average of price cost, emission cost, and grid cost in a mathematical form. To facilitate the optimization solving process, we linearize the model by adding and replacing the variables and constraints, including the net consumptions, state of charge, volatility, and the monthly statistics. Optimal charge or discharge actions can be obtained by solving this LP problem quite rapidly. However, the future information of load and solar generation is not observed in the current state. Therefore, to tackle the uncertainty of forecasting, we propose a stochastic optimization for daily dispatch. Gaussian noise is added on the predicted values to generate a multi-scenarios optimization problem, which we solve coordinately. In addition, several techniques of predictive model control have been involved. For example, the rolling horizon control. As we can see in the plot, at time step t, we predict and optimize for the next 24 hours. Then, after several hours, we take new measurements and correct the previous predictions and actions. This procedure is repeated for the full year. Another technique is the self-adaptive prediction adjustment to tackle the data drift issue. At each time step, we adjust the prediction by comparing the historical real values and the predicted values with this adjustment formula. Now we provide a brief summary of the empirical results. The best submission in online public leaderboard is a two-stage method of forecasting, followed by stochastic optimization with an average score of 0.728. We empirically show this method outperforms the equal certainty deterministic control and also the reinforcement learning. In the offline setting, we have tested the example of reinforcement learning and optimization in the training data. And ensembling according to time periods can gain additional improvements given the complete information. We note that the offline testing dataset is made based on the combination of average of training data. The hyperparameter tuning is conducted according to the performance offline, and also considering the 13 minutes online time limit. Finally, let me show our modeling and programming tool, MindOpt, which we use for data analysis and solving optimization problems. With MindOpt Solver, we can optimize complex systems for reducing costs and increasing efficiency. With MindOpt Studio, we can easily access the real-world decision-making issues and their solutions in this online platform. For more information, please don't hesitate to contact us. We are the Decision Intelligence Lab from Alibaba Damo Academy. Thank you very much for your listening.